Welcome to our lectures on the DC microgrid and control system. We are going to discuss today the microgrid dynamics and modeling. This is one of the important part of the control of the DC microgrid. So, our presentation layout will be introduction, there are the microgrid structures, mathematical analysis of the microgrid structure, DC microgrid dynamic modeling, micro sources dynamics in DC grid, the DC bus dynamic equation. These all will be discussed in detail in our discussions. Understanding our dynamics and using appropriate modeling methodologies are significant issues for microgrid control, synthesis and the stability analysis. Although the microgrid is a small scale, it has many complexities of the large scale conventional power systems. The dynamic analysis is required to ensure that the microgrid appears as a stable manner which controls the voltage and the frequency fluctuations. Particularly transition from the grid connected to the islanding operation mode may pose several challenges. So, we shall see that. Depending on the configurations, type, component, the microgrid dynamics may change and the different applications and different methodology may be applied or required. Now, incoming renewable based energy sources has been identified as generator of the clean electrical energy and are being encouraged worldwide over the conventional generator because of the carbon footprint, global warming, for many other issues. The increasing protections of small size renewable energy sources to existing grid has created a new sort of challenge for the power engineers. One of the most significant challenges is that this renewable energy sources generate either DC output or variable frequency or else variable voltage AC outputs. So, you have seen that in case of the wind turbine, that is by the variable AC. In case of your DC, in case of solar it is variable DC. In presence of these sources create a new challenge to maintain the stability of the existing grid also when you connect a microgrid with a fundamental grid. Therefore, suitable architectures is required to manage the power flow within the different micro sources and the storage element and the load within the grid. So, for this reason our figure 1 in this case represents the electrical equivalent circuits of a parallel converter microgrid system with the help of the suitable drop control along with the voltage and current control load on the microgrid can be shared in a desired ratio. You have DC 1 and DC 2. So, you can control over real power, imaginary power and the phase angle. Similarly, you can have a control over it and you can connect it to the same bus, and ultimately you can say that these two buses can be internally connected and thus you can control the flow of power from this point to this point or this point to that point. Because of the load and generator both are intermittent in nature. Previously load was intermittent in nature, now we have source also intermittent in nature. Therefore, a mathematical analysis of dynamics of microgrid will be helpful to developing the suitable control system. Dynamics of a parallel converter microgrid structures is shown in figure 1 is given as follows. The P denotes the differential function ddt and I is the specific converter. Dynamics of the individual converter in dq axis of the reference system is presented as B I S Q equal to M I Q plus L S I Q P into, this is the differential equations in the dq axis. This is for q axis and this is for the d axis, where we shall denote actually P as a form of the differentiation. It is a common notations, and I for the specific converter, it can be, you have a n number of converters. So, I can be 1, 2, 3, 4 to n. So, this is all about it. And dynamic equation of the transmission line between the two converter is given by, so it is a V m I q and minus V m I j, this is ith and the jth element. So, it is R 1 2 into I j q, so on. Similarly, it will follow through the D frame with just nomenclature will change, and there will be a cos component here, that is basically it will be D and this component will be q and cross component will be with the omega. A composite load has been assumed to be present as electrical load on the microgrid, which consists of linear, nonlinear, constant power type loads. The dynamics of these loads are represented as follows. So, P m I q equal to L I q plus L q, and with the term of the cross link, that is omega L I into I d. Similarly, you will have this term is cos link. So, nonlinear load equations, we can write it that nonlinear I q will be 2/3 of P in on M I q into minus actually it is basically P into V minus q into V divided by V square plus V d square plus V q square. Similarly, for the d axis, all the nomenclature will be changed to d, but this one will be minded, it will be a q, and for q it will be d, and for d this term will be q. So, for the constant power type sources, we have to model different kind of. So, ultimately what you understand constant power type sources, if voltage drop, then it will drag more current. So, this kind of sources, it will change little bit. Ultimately, it is 2/3 P I M I I q minus Q I M I d, and similarly it will be for the q axis. On the basis of the dynamic model of the parallel converter in the microgrid system, both transient and the steady state operation can be analyzed and performed. So, however, the microgrid operating in an autonomous mode will operate when voltage and frequency stabilization conditions is met. So, we have to see that once it is connected in aligning mode, you can have our own frequencies, and once you are connected to the grid, so you should have the frequency and voltage other stabilization condition, mean that otherwise it will be treated as a distribution of the disturbance of the sources. The development of the microgrid concept is based on the hierarchical distributed control architecture, where during the emergency situation an autonomous control should be able to run the system. You put it in the auto mode. Conceptually, there are two mode, there are two operating condition, one is grid connected mode that will govern, another is the aligning mode. in order to analyze the different operating conditions, it is necessary to address the particular issues related to the microsources and modeling and the controllers. The models needs to describe the dynamic behavior of microsources and their corresponding power electronics interface. This is an important requirement because since most of the microtechnologies that can be installed in the microgrid are not suitable for the direct connection to the electrical network due to its characteristics of the energy they produce. We cannot directly integrate your DC to DC, your solar inverter, your wind turbine into the grid. So, you require to have a gearboxes DFIG, thereafter you have a rotor side converter that will maintain the slip power. So, therefore, power electronics interfaces DC to DC, DC to AC, AC DC AC are required to needed to accurately modeled. The power flow between the different sources must be controlled in order to supply the real active power required by the grid power. This performance of the control of different power electronics converter and which require to be coordinated among themselves. So, consider a DC microgrid with a PV source, energy storage system and the grid supply. In order to design the control system of the PV source, the model of the entire system has to be analyzed. For the modeling of the PV based active generator, all the modulated values can be replaced by their average values during the modulation period. The equivalent electrical diagram with the equivalent average modeling of the power electronics converter, since you have there are two states by switching on and switching off. So, average model required to be considered, consisting of the PV system, the energy storage system, the grid connection and the DC bus is illustrated in the next figure. You see that this one, this is we will model it as a current source, thereafter you got an inductor and ultimately you got PV chopper, and this will be a current control voltage source. So, you got a DC bus and thereafter you got an inverter and you are feeding the power to it, and parallel you may have you are maintaining a DC bus and you are charging the capacitor. So, you can have the whole system in place. So, let us analyze it. The 3 power converter are used to introduce the control input of the each power conversion in order to control the power generated by the PV panels. To maintain constant DC bus voltage, to supply required power exchange with the grid and to ensure the power buffering of each storage unit. So, this is something we require to control these things, and thus we have this all these 3 converter topologies. So, now let us take PV power conversion system. The PV power conversion model, the PV panels are usually considered as a current source. We have discussed about the modeling of the PV cell. It is just, it will be now represented by the connection only, and it must be supplied by the voltage UPV, and the voltage comes from the filter, that is basically C1L1, which is fed to the modulated voltage of figure 3. So, this becomes the your PV power conversion system of the model, equivalent circuit diagram of the DC microgrid for PV power conversion. So, let us write the differential equations on the state space model of it. The inductor also modeled as a current source L1. The current depends on the PV voltage and the modulated voltage of the chopper output, that is UMPV. So, thus L1 LDI/dt equal to UMPV/T minus UPV. Losses in the filters and the capacitors are neglected. The capacitor C1 can stabilize the voltage Pb across the terminal of the panels. The capacitor can be modeled by using the PV current and the filtered current IL1. So, du PV dt equal to 1 by C ICPV. So, ICPV t equal to IPV minus IL1. ICPV is the injected current in the capacitor. The mean value of the terminal voltage of the chopper is obtained from the DC voltage and the duty cycle ratios. So, UMPV equal to MPV into UDC, IMPV equal to MPV minus IL1T. So, you got an energy storage system. In the model of ESS, and ESS is considered as a voltage source, that is a electrical storage element, and the voltage is USS, which is connected with the choke of the filter. It may be ultra capacitor, it may be the battery which connected to the choke of the filter, that is L2. So, ultimately this is the ESS and you got UDC here. So, similarly, by neglecting the losses of the filters, the dynamic equations of the filter current IESS expressed with the ESS voltage, UESS and modulated voltage. So, dl dt equal to 1 by L2 UESST minus UMSST. The mean value of the terminal voltage of the ESS chopper is UMSS is obtained from the DC voltage and the duty cycle ratio MESS. So, UMSS equal to MESS into UDC and MESS equal to MESS into ISS. The current ISS is modulated by the chopper, and this modulated current IMSS is injected to the common DC bus, and the voltage value of the output voltage is IMSS, and the chopper current is equal to the ISS current, and is multiplied by the duty cycle ratio of MESS. The 3-phase inverter within a choke as a filter is used for the grid connections. An equivalent modeling of the 3-phase inverter is sufficient to represent the fundamental component of voltage current of figure 5 as dependent on phase to phase voltage source, that is U inverter 13 and U inverter 23 within the DC bus voltage UDC via modulated indexes MINV 13 and MINV 23, and a dependent current sources INV with AC current through the same modulation index. So, you got an electrical diagram of the grid connections. So, you got IDC and thus you have two controller, that is RGLG, and it is feeding to the grid. Then mean value of modulated phase to phase voltage of the average current is expressed as UNV 13 equal to MINV 13 into UDC, UNV 23 equal to this modulation index into UDC, and thus the IMPV equal to this actually IMV 13 into IG1, that is the gate current of it, and IMV 13 into IG2. Assuming the gate voltages are balanced, so you have a more complexity when your grid voltage is unbalanced. The line voltage can be obtained by UINV 1 equal to 2/3 UINV 13 minus 2/3 UINV 23, UINV equal to minus 1/3 UINV 1/3 plus 2/3 UNV 2/3. The filter currents are deduced from the following equations. So, it is Ig1t equal to 1 by Lg, that is a grid inductor, IV inverter 1 minus Rg into Ig minus the grid voltage 1. Similarly, you can have Ig2 Gt equal to 1 by Lg inverter 2 Rg into Ig into Vg2. So, the 3 phase inverter voltages, grid voltages, current at duty cycle can be expressed into the vector form. These are the 3 voltages of the 3 inverters. So, this is the grid voltages, and that should be equal, and these are the grid currents, and these are the modulation index of this grid inverter. In this hybrid generating system, 3 energy sources, PV panel, ESS and the electrical grids are connected to the common DC bus via different power electronics converter. We have seen this thing in the figure number 2, please recall that. So, according to the DC coupling, the capacitor current IDC is expressed as Is equal to Im ESS plus Im PV. So, IDC equal to Is source plus minus Im inverter, where Im PV is the modulated current from the PV chopper and Im ESS is the modulated current from the energy storage chopper, and INV is the modulated current from the grid converter. So, thus we can express this DC bus current as your UDC T equal to 1 by CDT of T, and where CDC is the capacitor voltage of the DC bus. And we wanted to show something, like to go back in this figure 5, and you see that. So, this is the DC side of it, and this is the 2 inverter, or it can be taken as a one phase of the inverter also. Inverter is connected, that is inverter 1 3, that is generating the voltage, and this thing is a grid side inductor. Generally it is been placed inside the inside a solar inverter only, and of course it will come with some amount of the resistance. It is, please not misunderstood that as if it is a source inductance of the grid. It is generally physically connected into the system, thus this value is known to you. Similarly, for this other values, and considering that you can actually inject current into the system. So, you can have a 3 element here, 2 elements are essentially voltage and the current. So, here it is a source, and source is essentially consists of maybe the ESS and the IMPV, and the DC part of it, that is coming from the source, that is the DC source and the minus inverter. So, this is the combination of it. And let us go back again overall control circuitry, so that we can recall our system better. So, this is the figure number 2. So, now it is a IPV, and this thing is a UPV, and ultimately this is your PV chopper part, and here you got an inverter, and where actually your modulation index comes into the picture, and from this modulation index you have this inverter connected to a system, and you are injecting the power into the system, and thereafter this thing is your energy storing element, and this thing essentially a bidirectional DC to DC converter. So, it will be going through this. When you have a surplus power, it will store the mostly the battery, and it will take out the power once there is a there is actually energy deficiency into the local gate, and most of the this model is essentially generally coupled with the local resistances or the local load, then only analyze will be complete. Sometime we will provide a load here before the connections to the grid, so that it can also operate in the islanding mode. Thank you for your attention. We shall continue to our discussions with the DC microgrid in our next classes.